Dr. Mahdi Saatchi. He is going to talk to us about, and I thought I had it remembered, but obviously I don't, um, uncovering genetic signatures in Wagyu. So I know that will be a definite fun topic, and so here is Dr. Saatchi.
Good afternoon, everyone. I have a very good news for you. I'm the last presenting person here, and you will have a free time after this. So I would say at the beginning, I was like, oh, I have my last presentation, but I think these previous presentations set the table very well for my talk, so I can deliver the message today. So we're going to look at the genetic architecture of Wagyu, what makes this breed special. So because I'm the new face here, I'm trying to introduce myself. I'm showing here my pedigree, albeit my scientific pedigree. I did my PhD in genetics and animal breeding under supervision of Dr. Jawarami, University of Tehran. And then I came to Iowa State at 2010, where I did my postdoc research at genomics in beef cattle with under Dr. Dorian Garrick. If you look at this pedigree, all of them back to the Dr. J. Lush, who known as the father of modern animal breeding. So this is a proud to be related to this pedigree, similar what you proud to have the Wagyu special line. But I would say that creates some things that is maybe not good or bad or good, what we call it inbreeding. And this is something that I'm going to talk about today. I got some inbreeding in science and genetics. Maybe not bad because I stack and accumulate those good genes from Dr. J. Lush and thoughts, but I may not have that complete diversity about different discipline, different experience. So we want to see how that relates to animal breeding. So after I did my PhD and postdoc at Iowa State, my research was to how we can implement. Daniel showed that 2009 when the hosting started. So when I came 2010 Iowa State, that was early on the genomics adoption, and beef didn't have. So I worked with Dr. Garrick to help different beef breed associations to implement genomics for the early versions of the genomic applications. Then, after that, I went to working for PIC, Pig Improvement Company, for 2 years, but I didn't find a good flavor there, so I decided to back working with the beef industry. So since I back to Iowa again, I was working as an adjunct professor at Iowa State, as well as working with the group of the association, mainly Simmental, Red Angus, but the group that called IGS, or International Genetic Solution. As a genomicist helping them, there are about 20 or more than 20 different breed association here in US and international, Canada and Australia. I think they run multi-breed genetic evaluations, everything that doesn't include Angus, Hereford, and Wagyu, and Charolais probably at Hereford. Most of those breeds goes to the IGS, and I was part of that team. Not saying that I was competing with Georgia, we were good friends, but we were helping the other groups. And then I thought, okay, now genomics is kind of matured in those breed association. I thought maybe it's a time to bring some new tools and something that the breed association doesn't offer to the members. And that's why I established this company called Top Genomics, and trying to service different entity labs to design the genetic panels, as well as the breed association and different groups to adopt genomics technology. Today, we are having some new tools. We call them RightMate, Right Choice, or Right Bull, that are trying to achieve some goals that we are trying to also mention this in this talk. So the main talk is about the Wagyu and what's special about the Wagyu genome. We want to discover that by doing some studies. So I prepared some background. So I'm playing the video here that summary this study or research that have been done for the Wagyu. I'm sure that you will find it very interesting.
Hello, everyone, and welcome. It's great to be here with you all today. We're all here because we're passionate about this incredible breed. But what is it that truly makes a piece of American Wagyu beef one of the most sought-after steaks in the world? Well, the secret isn't just in the expert care and feeding. It's written right into their DNA. Today, we're going to go on a genetic journey to uncover that hidden signature that makes this beef so legendary. So let's get right to it. The big question we're all here to talk about is what secrets are really hiding in the American Wagyu genome? You know, an animal's DNA is its ultimate blueprint. And for a breed with such a unique, almost mythical origin story here in the United States, that blueprint holds some absolutely incredible tales. You know, the story of American Wagyu is a fascinating paradox, isn't it? Its elite status, its incredible quality, it's all built on a tiny, tiny founding population. After just a few key animals were imported from Japan back in the 70s and 90s, those genetic gates, they pretty much slammed shut. Now, this created a really unique, concentrated gene pool, but it also, as you all know, raised some huge challenges. So let's start by looking at that legacy. Okay, first up, a unique genetic legacy. We're going to talk about how this incredible breed was built from just a handful of original animals, and how we're now, right now, entering a brand new frontier where we can read their story right from their DNA. For decades, all of you have made incredible breeding decisions based on what you could see: pedigrees, EPDs, performance data. And let's be clear, that's powerful stuff. It's like a sports scout looking at a player's stats and past performance. But now we're shifting to genomic selection. This is a game changer. Instead of just reading the stats, we can now read the player's actual training manual, the DNA itself. It's the blueprint of their potential. And you know, as soon as we started looking at the DNA, the science threw us a real curveball. By mapping out genetic similarities, researchers found that American red Wagyu, the Akushi, is incredibly close to a Korean breed called Hanwoo. A total shock, right? But it's a perfect example of how genomics can uncover these ancient family ties that have been hidden for generations. So, how in the world do we actually read this genetic blueprint? How do we find the good stuff? Well, scientists use an incredibly powerful tool called GWAS to scan the entire genome and pinpoint the exact locations responsible for all those traits we care about. So, what is GWAS? Think of it like a superpowered find feature for the genome. It scans an animal's DNA looking for tiny single-letter variations called SNPs. You can think of these SNPs as little signposts on the genetic highway. The whole goal is to see if a specific signpost consistently points to a valuable trait, like more marbling or a heavier carcass. Here's how it works in a nutshell. First, scientists scan the DNA from hundreds, sometimes thousands of animals, mapping out all those genetic signposts. At the very same time, they're in the plant, precisely measuring every key economic trait from those exact same animals. Then they hand all that data over to some powerful computers to do the heavy lifting, finding which of those little signposts consistently show up in the animals with the best traits. And this is what you get. It's called a Manhattan plot, and you can see why. It looks like a city skyline. Every single dot is a genetic marker, a SNP, and the higher a dot is, the stronger its link is to the trait we're studying. Those highest peaks, the skyscrapers, that's where the magic is. Those are genomic hotspots that are screaming at us, hey, look over here, something important is happening in this part of the DNA. Okay, so that's the tool. Now for the really exciting part. What did this genetic search actually find? Let's get into the key signatures researchers have discovered for what makes Wagyu so special, from its growth all the way to that legendary fat quality. First things first, let's talk about what drives the bottom line, the genetic signature for carcass and growth traits. Finding the genes responsible for yield and profitability is, without a doubt, a massive step forward for all of us. And check this out. The results are incredibly specific. On bovine chromosome 14, researchers found a major genetic hotspot. And inside that hotspot are genes that we know help control muscle growth. So what does that mean in the real world? It means they found the specific bit of code that leads to heavier, more valuable cuts, like the chuck roll and the bicep. This isn't guesswork anymore. It's a precise address on the genome that says, more high-quality beef right here. All right, next up is the signature that truly defines Wagyu. What makes Wagyu? Well, Wagyu, fat quality and marbling. We all know Wagyu fat is just different. It has that lower melting point, that richer flavor. And now we're finally starting to understand why at the genetic level. And on chromosome 26, they found it, the Holy Grail, a gene called SCD. Now this gene is basically a tiny biological factory with one critical job. It converts standard saturated fat into those healthier, melt-in-your-mouth monounsaturated fats, or MUFAs. And researchers found variations right inside this gene that seem to turbocharge that process. This is the genetic engine that creates Wagyu's legendary buttery fat. So this is all fascinating science, right? But what's the end game? What does this mean for your herd, for your operation, and for the future of the American Wagyu breed? It's about taking these genetic secrets and using them to shape the future. What this research does is give you a powerful new toolkit. It means we can get more accurate genomic predictions for young animals, spotting a superior calf practically from birth. It means you can precisely identify and select for those exact high-value genes we just talked about. And so critically for our breed, it helps you manage inbreeding and maintain genetic health with incredible precision. It's about breeding smarter, not just harder. And as the researchers themselves put it, we are really just at the early stages of this journey. This isn't the end of the story, not by a long shot. It's the beginning of a brand new chapter where we can enhance selection for these desirable traits with more accuracy than ever before. So for the very first time, the genetic secrets of American Wagyu are out in the open. We can read the blueprint, we know what makes this beef so special. And it leaves all of us with a really fascinating question. Now that we can read the genetic signature, what will we, together, write for the next chapter of American Wagyu?
Okay, very good. So I think I tried to give you a little taste of what's make Wagyu different from what other researchers have identified and discovered, I think, and also what tools we are using usually to identify those. So basically, from literature, we know that there are a couple of genes that are special, as well as there are a couple of genes that are in common, but there are different mutations that we use. So here, we decided to also run similar genome-wide association study within the Wagyu association data. So Hannah asked me to collaborate on this project, so we get access to some genotypes, but 38,000 genotypes came in, and I got some EPDs as a phenotype, and as the video showed that when you want to run GWAS, you want to find what's the best SNP that associated with those high phenotype, which here is our EPD as the corrected phenotypes. So we found about 25 to 23,000, depending on the trait, EPDs that are matching with the genomic IDs that we use here. And I ran GWAS study on that, and here what I found. In chromosome 14 gene pop up as the main or most important genome region that are associated with this quality or growth and yield traits in Wagyu. We know that that piece of genome has the gene called PLAG1. That is a very old gene that has been discovered that associated with growth, not only in the beef cattle, in many other species as well. But there are also some other genes we identified that there are some good candidate genes related to growth or fatty acids metabolism that here are listed. But I think the main one that makes Wagyu not different from other breeds here, there is a variation you can still see in the Wagyu is due to the variation within this PLAG1 gene. Just to show you how it's different with the other breeds. This is the research when I was postdoc Iowa State interested to do was looking at the GWAS for different US beef breeds. Here in this publication, we studied about 10 different US breeds. You can see on the y-axis the name of breeds from Simmental, which is not only purebred Simmental, Sim Angus, crosses, Herdbook, Maine and Jew, and up to the Angus at the down. And then we look at different traits, which you see on the x-axis. And just to give you what that means, each circle here is the genetic variation for that trait in that breed. And each of those colored pie is the QTL, or the signature or piece of the genome that make that variation, that trait for that breed. As you can see easily, that we call it the blue gene, is the gene on chromosome 6 that are mainly the main contributor to variation of different traits in many of the continental and British breeds, mostly continental. You can see in the Simmental and other Gelbvieh breeds. Chromosome 14 gene is the yellow one, which is you don't see much on other breeds. There are some variation you can see in the Sim Angus population, but not much. But in the Wagyu, we see most of variation come from that gene. And these two group of genes, PLAG1 and chromosome 40, and the group of genes, we call it NCAPG and LCORE, which is two closed genes on chromosome C6. They are very, very known genes in terms of how those genes control in growth and height. Not, as I said, not even in the bovine. It showed they found in the human height are affected by these genes, as well as the horses, dogs, chickens. So these are very well established genes. But what you see here in the Wagyu, some of the variations you see in the yield and growth, carcass weight, yearling weight is due to the variation or mutations or SNPs that you can see different SNPs in that genes in this population. So how we use this information in practice? Okay, we know that there is a variation. We know that there are some large effect genes. One thing is that about adding another layer of information or confidence about the selecting bulls or heifers. Here I'm giving an example what the calving is. Maybe this is not a good example for Wagyu breeder. As I said, this is not an issue here, but when I present in this for many breeds, that's probably the main trait for them. But here, doesn't matter, any trait you consider, you're dealing with 3 bulls that they have same EPDs, okay? In the selection process, we're using EPDs, great tool, but if you screen those large effect genes for that trait, for example, here calving is, let's say the first bull you see that is a homozygote in the right direction for that trait, versus the second one is a heterozygote. You can see one of the genes are plus 2.5, the other one minus 2.5, and the middle one. And the bottom one is negative the opposite way. So when you want to select these bulls as a heifer bull or the calving is bulls, you probably will be more confident to selecting the first bull because this bull is not only have the great EPDs, but also right genes biologically proven for that trait. But what happened for the second bull? It's actually EPDs dealing with the average, bring you the average calf performance. But in reality, for the bulls that are heterozygote, for the large effect genes, you see some variation coming from those part of the genome because each bull has only one copy of his 2 copy of genes to his progeny within the sperm. So that means that bull, second bull, sometimes he passed the plus 2.5 gene, or sometimes he passed the minus 2.5. That means he creates some variation within these calf crops. So basically, in reality, he has 2 EPDs, but because we couldn't get an average of calf crop, we end up with the same EPDs. So this is how we designate these for other breeds. We call this is an ACE bull, so kind of biologically or genomically kind of verified calving is. Similar thing you do for the growth trait, for example. You have the same EPDs for growth, but you're dealing with different genotypes for those large effect genes. If you want to breed your cow, low-growing cow, one of these bulls, definitely you will pick up the first one because it's in the right weight with the right genes. We call them ATM because they generate more cash for the breeders. That's why we call it precision breeding. When it comes to mating decisions, not only using EPDs, which we should use, but adding the genotype information or DNA information help us to design the matings that is avoid the risk of creating a variation that doesn't in the favor direction. So we created a toolbox that we call it RightMate to help on using this kind of information. So it's basically genomic sorting tool or precision genomic mating tool that helps to decide or help to design the matings based on the DNA plus the EPDs. As I said, we have to have EPD as an estimate of all other moderate small effect genes, but we have to include those high impact genes. Also, we show that by using this, we can accelerate genetic gain improvement for any traits, not necessarily only marbling, trying always to make it balanced, but we can improve the index or all the trait that you're targeting in a shorter time. But more importantly, we can create more uniformity. If I knew that the cow is heterozygote and she is probably at risk of creating a small calf, I don't breed her to a heterozygote bull because there is 25% both past a small effect gene. So that's how we avoid we call it wasted mating. But I think most importantly for Wagyu breeders is managing inbreeding and genetic diversity. This is very important with this small effective population size that we have in here US for Wagyu breeders. We actually have the license to use the Mates software that is designed to optimize these features in breeding diversity and breeding objective customization. So we incorporate those RightMate and mate cell to deliver all of these features. So now I want to show you another video. This is the second story about, okay, we got this studied. We found some candidate genes. I have to say that these are early on research. We identified the PLAG1, other genes in candidate, but as mentioned, we are at the very stage of that. We have to deep more and find more genes as well as validate some of those large effect genes. But once we have this information, once we have these tools available for Wagyu breeder, what we can achieve with. So listen to this one.
You know, when you hear the words American Wagyu, you immediately think of the absolute pinnacle of beef quality. It commands a premium price for a reason, right? As breeders, you're the ones building that reputation. But with that kind of value, you've got a huge responsibility to protect it. So today, let's dive into exactly how we can do that.
And that brings us to the big question, the one every single Wagyu breeder is wrestling with. It's a real high-stakes balancing act. How in the world do you push for those elite traits, that incredible marbling, the tenderness, the growth, without, accidentally compromising the long-term health of your entire genetic line?
And right here, this is the heart of the challenge. We call it the Wagyu paradox. The very thing that makes this breed so incredibly special, its concentrated elite genetics, is also its biggest risk. We're all working with a gene pool that's, let's face it, pretty small. That means the danger of inbreeding, of losing that precious genetic diversity, is always there, kind of lurking behind every single mating decision we make. So, here's how we're going to tackle this paradox head on. First, we'll talk about what precision genome mating really is. Then, we'll see how tools like RightMate for seed stock producers and RightBull for commercial herds put it into practice. And finally, we'll look at the results, the proof in the progeny.
You know, the next big leap in breeding strategy isn't just about picking the bull with the highest numbers. We're moving into an era of true precision, and it's all powered by genomics.
So, what in the world is genomic mating? Well, to put it simply, it's a system that looks way beyond the pedigree, beyond just the EPDs, and it goes right into the full DNA profile of your animals. It uses that complete genetic blueprint to pair a sire and a dam for a very specific reason, to manage risk and, get this, to actually design the next generation, one calf at a time.
And this is a really big shift in how we think about breeding. Look, EPDs are fantastic tools. They're great at predicting what a bull's calves will do on average. Genomic mating, though, that's a design tool. It lets you get past the averages and start architecting a specific genetic outcome for a specific mating. It's kind of like the difference between forecasting the weather and actually being able to control it. Okay, let's zero in on the seed stock producers out there, the folks who are really truly shaping the future of the American Wagyu breed. So the key thing to get about a system like RightMate is that it's not about just chasing one single number. It helps you do two absolutely critical things at the exact same time. You get to push for rapid genetic gain in those traits that make you money, while you're actively managing and controlling inbreeding. You're not just trying to max out one EPD, you're optimizing the genetic health and the profitability of your entire herd for now and for the long haul. And this is where it gets really, really powerful. We can now actually identify specific high-impact genes. These are little stretches of DNA that have a huge effect on a single super valuable trait. By targeting these genes directly, you can make progress way, way faster than you ever could with just traditional selection. Let's talk about a perfect example for Wagyu breeders, PLAG1. PLAG1. Scientific studies have pointed right to this spot on chromosome 14 as a major player affecting carcass meat yield, specifically in Wagyu. This isn't a hunch. This is a known genetic marker with a direct, proven link to one of the most important economic traits in our business. So, how does this actually work for you? Well, it's pretty straightforward. First, the system identifies the PLAG1 status of all your sires and dams. Then, you can apply direct selection pressure right there in your mating decisions, basically stacking the deck in your favor. And the result? You accelerate your genetic progress exactly where it counts the most, on those high-value carcass traits. Okay, let's shift gears now and talk about the commercial side of the industry. This is for all of you producing those amazing, sought-after F1 crosses with Angus or maybe dairy cattle. For commercial producers, the name of the game is consistency. It's that simple. The goal is to create a uniform group of calves, high-quality, high-marbling calves that your buyers can absolutely count on. Driving down that variation and hitting that premium target over and over, that's what drives the profit. And that is precisely where a tool like RightBull is a complete game changer. It takes all that same deep genomic data and makes bull selection so much simpler. It helps you pinpoint the specific Wagyu bulls that are genetically wired to stamp out those high marbling F1s time after time. By looking at the full DNA, it helps ensure the right genes get passed on with maximum consistency. It's really about taking the guesswork out of your crossbreeding, which cuts your risk and gives your buyers the confidence to pay top dollar.
All right, so talk is one thing, but results are what really matter. Let's look at the hard data and see what this technology actually delivers out in the pasture.
Just look at these numbers. This is a direct comparison between calves from matings made with RightMate and without it. For yearling weight, you see almost a 3-pound advantage. Carcass weight, nearly a full pound heavier. And look at this, a big jump in the marbling EPD. These aren't just numbers on a page. These are real, measurable gains in the traits that directly hit your bottom line. And this quote from Tom Hook over at Hook Farms, it just brings the data to life. He says, you could see that you didn't have the bottom end. That's the whole point. He says the biggest advantage is taking out the risk. It's about getting rid of those bad pairings, those duds, and making your entire calf crop more uniform and way more valuable. So let me be super clear about something. This technology does not replace your experience. It doesn't replace your eye for good cattle. Like Tom says, you still have to do the cowboy logic stuff. This is a tool that comes alongside your expertise, and it adds this incredibly powerful layer of DNA-level data to help you make even smarter, more informed decisions. So to wrap this all up, what are the big takeaways? Well, first, precision genomic mating directly takes on that core Wagyu challenge of inbreeding. Second, it lets you target those high-impact genes, like PLAG1, to make progress faster. Third, it helps you create more consistent high-value calves, whether you're a seed stock or a commercial operator. And really, it all boils down to this: managing risk and protecting the future of your entire operation. And that really just leaves us with one final thought to chew on. With these kinds of tools in your toolbox, the ability to look deep into the DNA, to manage risk at a molecular level, and to target the exact genes you want to improve, what's possible for your herd? What will the next generation that you design actually look like?
Good. So just to clear that, as I said, we don't want to replace what you're doing. We are working as a partner to help to identify and avoid those risks that may come up with the matings. So basically, simply explain what the RightMate is. Start with a list of your candidate bulls that you pick. Let's say your 10 or 20 bulls that you have in mind you want to use for your breeding objectives. in your purebred line, and then you have your cow herd. So we use the APDs. We get the genotypes of your cows and the candidate bulls, and then we basically simulate or matching all the bulls to all the cows, all the combinations possible. And then the report that you get back would be, okay, out of these 10 bulls that you pick, these 5 or 6 bulls works for the first cows, these 8 bulls works for the second cow, and so on, because we check that those genes, that the combinations that are potential risk, we get out of the list. But what is the right bull then? The right bull is what we designed for group mating. So RightMate is when you individually mate a cow to the bull. But the right bull is when you want to use a herd bull or cleanup bull as the ranch bull. And then, or especially in case of F1, you want to use a Wagyu bull and a group of Angus or dairy females. Then among those bulls that are available, we search and find the bulls that match with that set of cows for that breeder or like a partners. In case of like integrated system, for example, they have 10 different commercial partners. We can help them identify the bulls that match for each of those breeders to be well, which maybe, I mean, customized different. The first breeder may have Angus breed that does have enough marbling, so he may need some help on growth. The other one may need more help on marbling versus the growth, so we can kind of manage and make it more uniform product. Because inbreeding and diversity is, I would think very important for the Wagyu breeders. I want to spend a little time tell you about these are not the same things first. When we were talking about inbreeding, it's basically a measurement that show how the genome of the individual is homozygote, that whose homozygosity comes from this common ancestor, same as what I showed on my pedigree. I get the same genes from J. Elish from the both sides of my pedigree. So if I'm homozygote for that gene, that percentage shows inbreeding, which is not always bad, as I said. If you got the right gene as a homozygote, that's what we want. That's always inbreeding is not a bad thing. Inbreeding become bad when it comes to the broken genes, the genes that functionally is not good for health or fertility or fitness. So if they become homozygote, then your cows or individual may not be functioning well or very healthy or robustness to different environment. So this is very important, especially when we talk about disease and coming and climate change, and we need to have animals that are robust for different, and that definitely inbreedings get them more susceptible and vulnerable to different environment. Inbreeding is not heritable, so if you have an inbred individual, you can manage that to bring down the inbreeding. It's not something that you heritable, but co-ancestry is a different thing. Co-ancestry is measurement that show how that individual is related to the rest of the population in that breed. And we want to decrease that co-ancestry because that also, this is the long-lasting effects, and that definitely related diversity. So if you bring down the co-ancestry, you increase in diversity. It means the individual in this population are less related to each other, which is what we want to have. So I bring you a question here that helps me explain that this genetic similarity. I'm showing you two pictures, one at the top at the left and the one at the bottom. Tell me which of these individuals in these two pictures are more similar. Are those two individuals, that white and black picture, they look similar to each other, or those two individuals at the bottom? Those that thinks the top group, they are more similar, raise their hands. A little. How about the bottom one? Yeah, more. That's what I was taught. So those two individuals at the top are white brothers, those that are invented airplane. So they are full brothers. I mean, we haven't tested genetically, but I'm sure they are full brothers. And also those bottom pictures showing two brothers again, that full brothers that won some of the scientific competitions. So basically, if you look at the phenotypes, sometimes the individual from the family, they're similar to each other, but sometimes not. The same thing in our families. Sometimes kids are very similar to dads and moms, but sometimes they're completely different. Sometimes you doubt that how that could be. But there are genetic reasons for that, and that's trying to explain it here. Let's look at one gene and assume that gene is heterozygote. If your sire is heterozygote and the dam is heterozygote, the progeny for that gene could be 4 different combinations. It can get A allele from the dad and A allele from dam, so become AA, homozygote AA for that gene. Or it can get A from sire, B from dam, become AB, and BA and BB. So 4 different possible. Let's say if a first progeny or calf is one of these. What would be the next one, second one? Again, could be one of the other one. If the first one is AA, the second one is AA, we say these individuals completely similar for this gene. They are both AA. That's why I put the number 1 there for that matrix, yeah? But if the first one is AB and the second is AA, they share half of the genome because they share allele A, but it doesn't share the B. So that's how I feel this matrix. And when I sum up this matrix, I come with the average of 50%. That's why we say in the pedigree, 2 brothers are 50% similar on average genomically. But we know it could be more or less, and that's why these differences come from, because we call it random shuffling of the genes. This is a slides from the paper that Daniela published a long time ago, if she remembers that. She was trying to look at that genomic similarity among the full-shape chicken. She had the access to the chicken data. She was looking at that, and interestingly, what she found here, the expected range is 50%, but you can see there are some full-shape, which means they are from same parents, but they are as low related as 20%, or they are more related at 60% or 70%. Definitely around the average, there you see more individual, but as you go away from average, there are less. So this is very important to know that how the genomics help us to improve the accuracy. And that's how the Daniela and Georgia use this genomic relationship matrix to make your genomic EPDs accurate. Because before using that, EPD based on the pedigree, always we put 50% relationship between embryos because they're always same pedigree. But now, once we have the genomics on those embryos, we know they are either 60%, 20%, so we can adjust those relationships and make it more accurate. So GRMN, or genomic relationship matrix, helps to improve accuracy. But here also, I think another application of genomic is to help us on manage inbreeding and diversity, because now we are able to calculate what we call it the realized relationship rather than what you expect by pedigree. So if I want to summarize what RightMate and RightBull can do for Wagyu breeders, I would say definitely they can speed up the genetic improvement for any trait that you're focusing on. Like, is it marbling, growth? Definitely we not recommend single trait selection, but we can optimize to make it faster, especially once we integrate those large effect genes in the calculations. Secondly, I think we showed in data, those data that I showed during the video was from the other breeds. Maybe this number doesn't make sense to you, but we showed that we make improvement. Those calf born from RightMate versus non-RightMate, they have advantage, but also the second benefits of these tools are making more uniform and consistent product. And most importantly, we say using these genomic tools, we are able to manage inbreeding more efficiently. We can help to avoid any depression of inbreeding that reduce the productivity as well as fertility and improve the herd vigor, as well as managing the genetic diversity, which is very crucial for long-term improvement and health of the Wagyu breeds, because as I said, this is a small genetic population that you're working. Definitely stack up very good genes, but there are always risks. If you don't manage genetic diversity, not only for health and productivity, talking just my previous presentation showed that there are disease coming, emerging. If there is not enough genetic diversity, it could be very dangerous. That's what happened to some, like a banana line that totally was fine. When the fungi come in, wipe out all the lines and there is no genetic left. Or what we're dealing with the hosting small genetic diversity problem. But also, not only for health, I would say for your future of your breed, there are some novel traits that are coming. We know the Wagyu is very specific for fatty acids and melting point of the fatty. So I have done a study at the other breed Angus population on the fatty acid profiles. We look at that if this is first, if there is enough variation, genetic variation among the fatty acid of the beef, like omega-3, omega-6, cholesterol levels, and all of those healthy and unhealthy, would call acid profiles. And we found actually there are genetic variation, although the nutrition impact, but very interesting that is very highly heritable, 57 heritability of some of those traits. So there are some traits we don't measure, but once AI comings and technology is coming, we definitely have new novel traits that we can measure to and select for, specifically for this legacy breed. But we don't want to lose the genetic diversity. If you're just focusing on using certain lines and not taking attention to the diversity, you may lose some good genes down the road that can put Wagyu again special for those traits as well. With that, I would like to thanks again for AWA staff for collaborating and inviting me to come and present some of the research and the tools that we developed, and also your time, and would be happy to take any question that you may have. I try to make it simple. That's why I made those videos. Those have better accent than my accent, so I know that they can talk. I know that Daniela.
Very nice tool, Mahdi. I just have a curiosity, actually. So what is the percentage of additive genetic variance explained by Plague 1 in Wagyu?
So depending on how you define it, if it's a single SNP or QTL regions, that percentage varies. But something that we found, it's not as big as those other breeds that I showed you, that like 20%, 30%. Here we're talking about 2%, 3%. And that's why I didn't want to get too very complex, but because of this small effective population size we're dealing here, there is a high, we call it linkage disequilibrium, OLD, which means the genome of Wagyu transmitted as a big chunk rather than random shuffling. And that once they are linked together as a big blocks, when you want to look at this, assume that in the high row that all the signs pass together. So it's hard to find a specific sign that's associated with traits. So that's why the effect of the Plague 1 gene or other genes will be distributed among all of those signs rather seeing this highest coverage. That's because of the nature of the data, but we are very confident that there is a mutation and variation in Plague 1 gene that is important for Wagyu growth. Yep, question over there.
Hi, yeah, I've had the privilege of having a sneak peek at the RightMate program, and I was pretty impressed. My question to you is, when will it be available for the AWA members to use?
So definitely, I mean, always there we can make it better, added more features to make it better. I would say, I mean, we plan to have it ready by end of the year. hopefully by that time we have also the indices, because once we have indices, we can optimize on index, but we are not have to wait to get those indices because we can prioritize or customize the individual traits to get this. I think most importantly, we can manage diversity and breeding from now. But I think it should be ready by before the end of the year. Over there, yep.
First of all, Shatari, have you worked?
Thank you. Oh, Chitori. I know, I got it. How are you doing, Min?
Good. Have you done any research on Exxon 5? I know that the Japanese are really hot on that, and we can't get that testing here.
Exxon 5?
Yes.
No, I haven't seen anything in this data we look. Maybe because first thing, I think I showed you, we are using 100,000 markers, mostly in that, because the current chip available GGP, we call it 100K. There were others that we imputed up. But the genome of the cattle have 3 billion of SNPs. So we just sampled 100,000 of them. We hope that these markers that we picked that are, even they are not actual mutation, they are close enough to those mutations that can use that, we call it LD or linkage as a block to give us the signals and direct us to the region. Maybe those markers are indeed that didn't have enough for linkage with those markers you were talking about in our data, but no, I haven't seen that. Good point. From this side? I see no question. Okay, thank you so much. Have a great evening.